let's talk about some examples of applications of Monte Carlo approximation to sort of get a feel for what types of things, what types of situations are appropriate for Monte Carlo, and also to start to train our mathematical eye to recognize how to apply a Monte Carlo approximation. So the standard, maybe sort of first example that people use is estimating pi, approximating the number pi by looking at this sort of quarter disk here and and then drawing a bunch of samples uniformly from this square and then counting, you know, what fraction land in this sort of quarter disk and then approximating pi. But that's kind of boring. I didn't want to. I think it would be much more interesting to try to approximate the area of the Mandelbrot set. So of course this is the Mandelbrot set. I'm sure you're all familiar with, at least have seen it before. And so let's, for our first example, think about the area of the Mandelbrot set after Benoit Mandelbrot. Now a technical point which arises here is the question of whether the Mandelbrot set has an area. In other words, is it a measurable set? Does it even have a well-defined thing called an area? And it turns out it does. It is actually a compact set. It's a compact subset of the complex plane, or you could think about it as a subset of R2. And since it's closed, it's therefore Lebesgue measurable. And since it's compact, it has a finite measure. So this is a well-defined problem to try to figure out what this area is. And so I looked that up. I know that from Gamlin. Gamlin has an excellent little textbook on complex analysis. And another thing which Gamlin tells us is that the Mandelbrot set is contained in, maybe something like this, contained in the square from -2 to 2. I think this is probably not centered correctly, but you get the sort of rough idea. -2 to 2 in each direction, where 0 is, I don't know where it is exactly. I don't know if it's here, somewhere around here. And so let's call this square S. S is -2 to 2 cross -2 to 2. And let's call the Mandelbrot set A. So the Mandelbrot set, I haven't really defined it yet. Let's write down what the definition is, just to be clear. The Mandelbrot set, so we're all on the same page. It's the set of complex numbers C such that the sequence Zn is bounded. I write BDD to abbreviate bounded, where this sequence is defined in the following way. Z1 is 0, and Zn plus 1 equals Zn squared plus C, this constant, the constant C. And so each complex number, for each complex number C, this defines some sequence. This iteration defines some sequence. And it's in the set, C is in the set, the Mandelbrot set, if that sequence is bounded. That's the Mandelbrot set. Very, very extraordinarily simple. So we want to compute the area of this thing, M of A. M for measure, M for Lebesgue measure. Area is sort of our intuitive notion for Lebesgue measure, and Lebesgue measure in 2D, 2 dimensions. And so how are we going to do this? Let's think about, you know, what we'd like to do to use a Monte Carlo approximation is to somehow write this in the form of an expectation. And how can we do that? Well, maybe we can think about it as a probability. Every probability is an expectation. So what if we think about the measure, the area of A divided by the area of S, so the fraction of this square occupied by the Mandelbrot set. That's some fraction, that's some number between 0 and 1. We can think about that as the probability that a uniform random variable in S in the square lands in the Mandelbrot set. So this is a probability. And the measure of S is, of course, well, it's 4 by 4, so the area of S, the measure of S, is 16. So this equals, well, it equals that probability. Let's write the probability first. This equals the probability that a random variable x uniformly distributed over the square lands in the set A. And this, of course, is the expected value of the indicator that x is in A. And so we can approximate this, right? We can use a Monte Carlo approximation for this. So we know, remember, we know that that the area of S is 16. So let's do this. So let's approximate the measure of A by 16 times this guy, or 16 times our Monte Carlo approximator for this. So that's going to be 16 times 1 over n times the sum, as I goes from 1 to n, of the indicator that xi is in the Mandelbrot set, where xi is uniformly distributed over the square S. And here also x was uniformly distributed over the square. So we draw these n, if we draw n uniform samples from the square, you know, I hate to sort of draw on this, but if we were to draw n samples uniformly, then what this is saying is just count how many of your samples land inside the Mandelbrot set. So I don't know, it looks like maybe 5 here. Count how many there were out of the total number of samples, n. Take that fraction, multiply it by 16, and that's your approximation. That's your approximation for the area of the Mandelbrot set. So this would be a Monte Carlo estimator for that area. And this is the cool thing, because, you know, if you were to think about, I mean, this is a super, super complicated set. So, you know, your first approach to doing this, if you didn't know about Monte Carlo, might be to sort of discretize this square and, you know, just evaluate for a whole bunch of points in here at some fine grid. But there's sort of a problem with that, or there might be a problem. I don't really know well enough, but you know, there might be some structure in here that if you were to draw, you know, some grid of points, that you might just somehow be biased in your estimate of the area. You might happen to land more times in the set than you should have along these boundaries here. So it's not really clear whether, you know, you really get the same guarantees using this sort of discretization as you do using a Monte Carlo approximation. And it's super simple. Okay, so that's example number 1, and I think that's a neat sort of example. All right, so that's the first example, and here's another example. Something about, so if we want to, so you can tell from the picture, it's going to be something about finance probably. If you can read that, I don't know if you can make out. It says Dow Jones Industrial Average, and this is a chart of the Dow Jones Industrial Average, the index, from around 1900 to, I guess, a little past 2010. It looks like it's up to date here, 2011. And so for our second example, let's think about computing the expected return on some investment strategy. So let's think about expected returns. Now, I'm not by any means an expert in finance, and so this is, you know, I'm well out of my area of expertise here, but I just wanted to give you sort of a very, very crude, rough idea of how Monte Carlo can be used for this type of thing. So let's say that you have some different investment strategies, and you want to evaluate their performance over, say, the next 30 days. So you discretize the next 30 days into a bunch of sequence of time steps, 1 to, let's say, capital T. And you have some measure of the market activity. Maybe it's, I don't know, maybe it's the Dow Jones, something like that, but it could be something more complicated. At each of those time steps, x1 to x capital T. It could be a whole vector of stock prices and indices and who knows what. And so this is your sort of the state of the system. And you model this as a random vector or some random process, x1 to xt with some, you have some model P here. Maybe it's a Markov model, who knows? Maybe it's a second order, higher order Markov, all kinds of complicated, crazy stuff going on in here. And then you have a strategy, S, or a bunch of strategies, S, and each of those strategies gives you some return. Let's put that over here, some return on a given vector S, and so you would like to know what is the expected return. So you want to compute this expected value of the return of the strategy S. So let's call that R of S, little r of S. It's the expected return of strategy S. And this, let's say this is maybe you've discretized the space that these x's all take values in also. So this is some huge sum over all these x1, maybe I'll use x1 colon t to denote this vector, this sequence. It's this huge sum over all these possible values of the return on that sequence times the probability of that sequence. It's an expected value. And so we can approximate this by 1 over n, just the usual thing, I from 1 to n, of the return on the random sample, let's call it x superscript I, 1 to t. So each of these random samples is a sequence x1 to xt, and each of them is drawn according to this distribution P. So you draw these n sequences. So you have some model here. You run your model n times. You get n different sort of worlds that might happen. And then in each of those worlds, you evaluate the return of the strategy S. And you get your Monte Carlo approximation for the expected return of that strategy over the next 30 days. Now the thing which is sort of interesting about this, so maybe I should have mentioned also about the previous one, the thing which is interesting about this, the reason why you might want to do a Monte Carlo approximation here, is that this model could be super, super complicated. This could be some crazy model and you have absolutely no hope of evaluating this analytically, because this is some humongous sum here, and you could never ever hope to evaluate this sum exactly. And furthermore, your strategy might be super complicated also. It might be some crazy thing where you're looking at, all kinds of, whatever's going on, and so this sum could just be totally intractable. And that's why you might want to do a Monte Carlo estimate for this. It's almost, it's trivial. You just run your model n times and you evaluate the outcome and you approximate it. And maybe I should have mentioned here also, so the reason why a Monte Carlo estimate might be a good idea for this area of the Mandelbrot set is that this is a super, super complicated function, right? It's insanely complicated. And you have absolutely no hope of, I don't think anybody's done it. I don't think there's a way, or there might not be a way to get this exactly, to analytically compute the area. But it's super easy to approximate with Monte Carlo. Okay, so those were just a couple examples of Monte Carlo approximation.